All right, with this video, we're going to study two more tests for series, and they are the ratio and root tests. So first we have the ratio test. And so we're going to look at a series from 1 to infinity of a sub n, where a sub n is a ratio. And when I say ratio, I mean like rational, like it's got a top and a bottom, so it's a fraction, with non-zero terms. And when you do the ratio test, the things that you're going to look for in the problem, because this isn't the only type of series where we've had a ratio before, so the things that we're specifically going to look for is factorials, or multiplication patterns, other than like geometric series, of course. All right, so the way that we do the test is we take the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. So a sub n plus 1 is just taking the series itself and adding 1 to all of the n's in the problem, and then you're dividing it by the series itself, and what you'll do is you'll simplify, 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 and eventually get to the point where you can evaluate the limit. And we have three different types of conclusions that we can get based on what the evaluation of the limit is. So if we get a limit that is less than 1, then our conclusion is that it converges absolutely, and we actually say converges absolutely. We use those words. If it equals 1 exactly, then our conclusion is there is no conclusion. Conclusion. And we must use a different test. And if the result is greater than 1, then that means that the series diverges. And that includes infinity. So sometimes students will ask me, what if the limit is infinity? Well, that's greater than 1, so it diverges. All right, the root test is when the sum from 1 to infinity of the sequence where, or not of the sequence, sorry, of the series, where a sub n is a root. And so what we're going to look for here is we want everything in the problem to be to the nth power, because then we can take the nth root of the problem. So we're going to say everything to the nth power. All right, so here we're going to say the limit as n goes to infinity of the nth root of the absolute value of a sub n. And again, we have three conclusions. So if the result of the limit is less than 1, then it converges absolutely. If it equals 1 exactly, then we have no conclusion, and we have to do, I missed the kind of conclusion. Oh, goodness. We have no conclusion, and then we have to use a different test. Gosh, that's funny. And if it's greater than 1, then it diverges. All right, so I've already kind of mentioned this, but we'll write a special note on our paper. So when you're using the ratio or the root test, if the series converges, you must state that it converges absolutely. So for these tests, there is no such thing as conditional convergence. It has to converge absolutely. All right. Now the ratio test is one of my favorites, honestly, and it's a very common test. It's one that we will use a lot, especially next unit. So here we're going to do some examples, and the instructions for our examples are going to be to determine whether the series converges or diverges. All right, so example 1, we're going to do 2 to the n over n factorial. And so when we look at this problem, we see that it's a ratio. I do see an nth power, but I also see a factorial. And so this is a ratio test. All right, so I'm going to say the limit as n goes to infinity. I've got my absolute value. I have 2 to the n plus 1 over n plus 1 factorial divided by 2 to the n over n factorial. All right, now what I would say on these, because as you do more and more of these problems, you're going to be tempted to show less and less work. So I'd say when you start off doing these problems, show all of your steps so that you don't make little mistakes. And then if you are doing the problems right consistently and you want to shortcut some steps, then you can. All right, so next, I have a fraction divided by a fraction, so I'm going to keep it, change it, flip it. So I'm going to write limit as n goes to infinity. Keep the top the same. Change it to a multiplication problem and flip the bottom up. All right. And then what I'm going to go ahead and do now is I'm going to think about the different parts that I can like simplify or think of in a different way. So 2 to the n plus 1 is the same as 2 to the n multiplied by 2 to the 1. It's just like they multiplied the bases, and so they didn't multiply the bases, but when they multiplied them together, they kept the base and added the exponents. So that's another way of thinking of that one. And then if we think of factorials, we know that n plus 1 factorial is n plus 1 times n minus 1 times n minus 2. N factorial is n times n minus 1 times n minus 2. And so n plus 1 factorial can actually be written as n plus 1 multiplied by n factorial. That's another way of thinking of that. And if that doesn't make sense to you, then let me know tomorrow in class and we can make a list of some of the factorials and how to think of them to make the ratio test a lot easier for us. So now that I have that written down, I can go ahead and look at the different things in the problem that are going to cancel out. And so I can see that my 2 to the n is going to cancel out. And I can see that my n factorial is going to cancel out. And then I can go ahead and write my limit with the stuff that I have remaining. So I have the limit as n goes to infinity. And all that I have left on the top is just a 2. And then all that I have left on the bottom is that n plus 1. And so if I evaluate that limit as 2 over n plus 1, where the n is going to infinity, that would definitely be 0. 0 is less than 1, and so my conclusion with this problem is that that series converges absolutely. All right, let's try another one. So, example 2. For this one, we're going to have n squared times 2 to the n plus 1 divided by 3 to the n. So, again, this is going to be the ratio test. I can tell because it's a ratio. It's clearly not geometric. Root test isn't going to work because we only have one thing to the nth power. It's not alternating signs. Integrating that would be a bear. So this is the ratio test. And so I'll go ahead and get it set up. We're going to do the limit as n goes to infinity of n plus 1 squared times 2 to the n plus 1 divided by 3 to the n plus 1. And then we have n squared 2 to the n plus 1 over 3 to the n. Okay. And I usually write that first step small just because I know I'm about to keep it, change it, flip it. A lot of students, when they first write this, instead of writing this step, they just do the keep, change, flip step. Again, I would say don't skip things until you've done enough of these to not make mistakes. Okay, so I'm going to keep the top the same. So I have n plus 1 squared, 2 to the n plus 1 plus 1. I'm going to go ahead and leave it like that. I'm going to leave it like that. Over 3 to the n plus 1 times 3 to the n over n squared, and then 2 to the n plus 1. All right, so if I kind of think about splitting these things apart, this one is going to be 3 to the n times 3 to the 1. This one I can think about because my goal is to have this cancel, so I can think of this one as 2 to the n plus 1 times 2 to the 1. And so now I can go through and do my canceling. So 2 to the n plus 1 cancels. 3 to the n cancels. One of the biggest mistakes I see students make is thinking that there's any sort of canceling that can be done here, and that is just not the case. All right, so make sure you do not cancel those. Okay, so what we have now is we have the limit as n goes to infinity, and my leftovers, I have the n plus 1 squared on the top, and I also have a 2. So I have 2 times n plus 1 squared on the top, and then on the bottom I have a 3 and an n squared. All right, now some people are going to be pretty comfortable with evaluating this the way that it looks right now. If you are not comfortable with that, you can go ahead and continue and see what happens when you FOIL out the n plus 1 squared. So I'm going to go ahead and continue just so you can see all of my thought process. So I have the limit as n goes to infinity of 2 times, and if I write n plus 1 out twice and FOIL it, I get n squared plus 2n plus 1. And I'll go ahead and do one more step. So that would be 2n squared plus 4n plus 2 over 3n squared. And so when we evaluate limits, we only care about the biggest part, so the degree basically. The rest of it is not going to be big enough to make a difference. And so since the n squareds are the same size, that means the infinities would be the same size and they would cancel, and this is going to give me a result of 2/3. Now you can definitely see that back here if you can picture in your head what would happen when you FOIL it out, and so you can see the 2/3 right there. But if you need to keep going in the problem to get to the 2/3, that's not a problem. So this is less than 1, which means it converges absolutely. All right, let's go ahead and do the next problem. So for this one, we have -1 to the nth power, square root of n, divided by n plus 1. All right, so again, this is going to be a ratio test. And so I'm going to go ahead and say the limit as n goes to infinity of -1 to the n plus 1 square root of n plus 1 divided by n plus 1 plus 1, and then -1 to the n square root of n over n plus 1. All right, so in here, you can already say, since this is within an absolute value symbol, that your alternating idea, that your alternating signs is not going to matter because we have an absolute value sign around this. So I think in my answer keys, I tend to just deal with the -1 and like keep it going and use the rules on it, and then just show eventually that the absolute value gets rid of it. But if you want to get rid of this -1 from the very beginning, you definitely can because it doesn't make much difference in the problem. So I'll go ahead and show you the same way that it will probably end up looking on my answer keys. So I'm going to say the limit as n goes to infinity. I'm going to do the keep, change, flip, and I'm going to leave that -1 there. So -1 to the n plus 1 square root n plus 1 over n plus 2, and then n plus 1 over -1 to the n square root n. All right, so here I went ahead and simplified this, and this actually, well, you can go ahead and do it. Times -1 to the 1. You can see that they'll cancel out, and you end up just getting a -1 to the 1 power. And then with the rest of it, we can't cancel any of that stuff out because all of that's different. So we have to keep everything. So next I'm going to go ahead and say the limit as n goes to infinity. And on the top, I have the -1 and the square root of n plus 1 and the n plus 1. And then on the bottom, I have an n plus 2 and a square root of n. That's everything that's left. And if I look at this, the -1 in the front, it's an absolute value, so that's not going to do anything. So I can ignore that. So if you wanted to get rid of it in the beginning, that kind of makes more sense, I guess. Okay, so if we can picture thinking about just our highest exponent on the top and the bottom, this is kind of like an n to the 1, this is kind of like an n to the 1/2. I know that when I plug in the infinities, they're not going to do anything with the 1. The 1 is going to be so small it won't make a difference. So it's kind of like we have an n to the 3/2 on the top. Same thing on the bottom. The 2 is not going to make a difference. We're going to have an n to the 3/2. There's no coefficients for any of this, and so the limit of this is actually going to be 1. So we just did all of that work for no conclusion. Which means we have to do the problem another way. So I'm going to go ahead and do the alternating series test. I don't know why I was going to draw a capital T like that. That looks silly. Alternating series test. Okay, so the limit as n goes to infinity of the square root of n over n plus 1, the exponent on the top would be a 1/2. The exponent on the bottom is a 1, and so that means that this limit is 0. So that's check, first part. The second part of the alternating series test would be that the square root of n plus 1 divided by n plus 1 plus 1 would have to be less than or equal to the square root of n over n plus 1. If you ever are unsure about this, you could just go ahead and graph these. So if it's a calculator active problem, you could go ahead and graph each of these on your calculator, and you would see that this curve is underneath that curve. So we do know that it's less, so check. And so now I just need to see if it converges absolutely or converges conditionally. So I'm going to go ahead and do the limit comparison test with the square root of n over n. So if I was to simplify that, n to the 1/2 on top, n to the 1 on the bottom, this would simplify to 1 over n to the 1/2, which is a p-series. and it's a p series where the p is 1/2. And so that would mean that by what we think of with the p series, it would diverge. So now I'm going to go ahead and do the limit as n goes to infinity of the square root of n over the square root of n plus 1 divided by the square root of n over n. And so that's the limit as n goes to infinity of square root of n over n plus 1 times n over the square root of n, and those cancel. And so we have the limit as n goes to infinity of n over n plus 1 equals 1. And here, remember with the limit comparison test, it's not an issue if it equals 1. It just tells us that it equals a number. And so that means that we can conclude that this converges conditionally. All right, and then we're going to go ahead and do one last example because we have to have a root example. So for this one, we're going to say n equals 1 to infinity of e to the 2n over n to the n. And finally, we have a root test because we have something where we have things to the nth power. So I'm going to say the limit as n goes to infinity of the nth root of, and here I have the absolute value of e to the 2n over n to the n, right here. And so if I think about simplifying this, that means I have the limit as n goes to infinity. If I take the nth root of 2 to the n, then that's kind of like saying I have e to the 2n over n to the n over n. So if you think about the way that your exponents work when you're converting back and forth between radicals and rational exponents. And so this is going to be the limit as n goes to infinity of e to the second power divided by n. And if I plug in infinity there, I'm going to get 0. And 0 is less than 1. And so my conclusion here is that this converges absolutely. Now, as easy as that was, this test is not as common. So I would say the test that is definitely more common is the ratio test.